And let's move right now to the second speaker. And the second speaker will be Iosif. Iosif, are you with us? Can you hear us?
I hope so.
Yeah, we can see you and hear. So, yeah, I guess you can start and I will go on mute.
Thank you. Hello, everyone. Very nice to have opportunity to speak to you today. Thanks a lot for joining today's meetup. My name is Iosif Itkin. I'm CEO and co-founder of Exactpro, and today's presentation is dedicated to high-volume automated testing. Let me check if I can switch the slides. Sorry. I think it is necessary to make me a speaker for me to be able to move back and forward. Is it possible to do it?
Yes, sure, Iosif. I guess we need a support from our IT. Just a second, and you will be able to move the slides.
Okay.
Sorry for this.
No.
Yeah, can you please try once again right now? You see the slides, yeah?
I can see the slides.
And
but
can you click on them?
No, I can't move them.
Okay. Before IT makes you, yeah. Now you're a presenter and you can, yeah.
Thank you.
Okay, great.
Thank you very much. So, sorry for delay and technical difficulties. It's not possible to do everything without them. That's why we have software testing in place. So Exactpro is focused on software testing and software development for mission-critical fintech systems. We are headquartered in UK. We have operations in US, in Georgia. We plan to open offices in 2 more countries this year. Exactpro employs over 630 specialists. Our work is well recognized by the industry. We have recent awards in 2020 and 2021 for managed support services, for operational resiliency, for automation technology, for our team management, and also for the work of global exchanges divisions and the head of global exchanges division. We work with clients in more than 20 countries on all continents apart from Antarctic, and we provide processes, platforms, and people to half of top 20 global exchange groups. Most of our clients are regulated by Bank of England, Financial Conduct Authority, or their counterparts in other countries, relevant counterparts. And we deal with the systems, mission-critical infrastructure, and there are many challenges to the operational resiliency of such systems, from technical innovation to changing environments, and especially system complexity. So complexity of the systems increases, and it requires special processes, platforms, and special people, of course, to be able to explore more sophisticated software and provide information about its quality to do software testing. The problem statement. Technology is getting more and more sophisticated and distributed. Data volumes and complexity levels of the software are increasing. To survive and thrive in a changing world, we need to understand technology around us. Software testing is our first, last, and the only line of defense against unknown problems in the software. Adequate processes, platforms, and people are required to understand, build, transform, and operate modern technology. And one of the processes that I would like to cover today is called high volume automated testing. There are two different ways of formulating it. It is high volume test automation, HVTA, or HIVAT, high volume of automated testing. The work in this area started in 2003 by presentation, by workshops, by Kem Kainer on the subject. There was also continuation of it 10 years later in 2013. I'm not sure why this very relevant topic only appears once every 10 years. I believe that high volume of automated testing is certainly the future of software testing, the future of technology. So it's likely something will also appear in 2023. I highly recommend to you to look at the website with an overview of high volume automated testing and also a presentation on the subject. There are various types of defects that high volume automated testing can help to uncover that are more prone to be hidden from other types of software testing. First of all, there are special narrow conditions that are not happening for every value of large domains, subdomains of values. There are some things that lead to problems only in very specific conditions. And when we go through many permutations, we are more likely to hit these particular problems. Also, the definition of what is narrow and what is special is context dependent. Very often something that you consider to be very specific or very narrow or very unrealistic, when it does happen in production, it leads to severe impact and severe problems. So ability to catch low frequency, high risk, and high impact problems before the go live is very important. Then HIVAT is very good at helping to identify timing related errors. So when quite often in low latency environment in particular, events can have different sequence for different repetition of the same scenario. And high volume automated testing helps to identify race conditions, deadlocks, and other things. And also, of course, by executing high volume of something, we can uncover problems related to corrupt memories, stack, and internal states problems, and of course, resource leakage. More references. So there is a nice presentation that is called How to Actually Do High Volume Automated Testing. Please have a look. It is available on SlideShare. There's a video, High Volume Automated Testing, describing practical application of the approach to the system with surveillance cameras and many combinations of locks, etc. And another nice presentation on the subject that contains a very good summary of larger documents is called High Volume Automated Testing. And it contains the actual definition present on the slide. So HiVAT is a family of test techniques that enable a tester to run and evaluate arbitrarily many computer-assisted tests. So before we will dig deeper into this definition, let's look at the bigger picture. So what is software testing? Software testing is exploring software with the intent of finding bugs. Software testing is an empirical technical investigation conducted to provide stakeholders with information about the quality of the product or service under test. So software testing is information service, and good software testing is based on scientific method. We study reality, we study software reality and uncover information about software. We observe, we ask questions, we formulate hypotheses, we use them to structure experiments against the system under test. And based on the outcome of these experiments, we make conclusion. And then we repeat it on the next level, trying to uncover more and more information about the system. So robots or machines are not able to do it, first of all, because they can't be bargained with, they can't be reasoned with, and they can't do anything intentionally. So intention requires emotions and will to do something. So it is not something that machines have at the moment. So the most important test instrument is, of course, the human's brain. So it is the main test tool that we have. Unfortunately, the software tester's brain is relatively small, and our capabilities are limited. It means that the human's capacity to design tests is also limited. So when we do it, we will get to the small number of fixed tests due to our innate capability of humans to do things. But humans, we have ability to extend our abilities by using tools to make us stronger in various areas. And in particular, we can try to use computer assistants to support us in designing more things. Automated testing is computer-assisted testing, where we use additional support from the tools to do exploration, that is software testing. And so the working definition of high volumes of automated testing, it is a family of test techniques that use software to generate, execute, and interpret arbitrarily many tests. A family of test techniques that empower a tester to focus on interesting results by using software to design, implement, execute, and interpret a large suite of tests, for example, from thousands to billions of different tests. So we rely on computer aid to design not a single, not hundreds, not thousands, but more and more scenarios. So what can we do? How we can increase the number of tests? One simple approach, very simple approach, is when we already have like a regression library of hundreds or thousands scenarios. What we can do is we can execute it multiple times. So will it lead to any additional information, to any additional defects? So say we'll take only past scenarios from a large regression library and we'll start running them again and again. There is a quote that is, sorry, there was a quote. There is a quote that is mistakenly attributed to Albert Einstein, that the definition of insanity is doing something over and over again and expecting a different result. You can use the link above to get more information about the quote. But the idea whether repeating the same test twice would be doing something over and over again. So whether it is repeating the same thing or not. Say, example, a simple example, if we'll take a light bulb and we can turn it on and off. We can turn it on and off. And it looks like something very, very simple, like one bit of information. But if when we turn it on and off, the effect for consequent attempt will be different from the first attempt. And also it will depend on many other things, because in reality, as with many other systems that are complex systems and even simple systems, they do have internal state that changes when we perform particular sequence of steps. There is a famous job interview question about light bulbs. It says, you are in a room with 3 switches which correspond to 3 bulbs in another room, and you don't know which switch corresponds to which bulb. You can only enter the room with the bulbs once. You cannot use any external equipment, power supplies, resistors, etc. How do you find out which bulb corresponds to which switch? And this one is allegedly frequently asked at the job interviews. And the answer is that what you can do is you can switch one of the bulb for some time and turn it on for some time, and it will become hot. Then you will turn off the switch and turn on another one. And when you go into the room, you will have one bulb that is on, one that is off, and one that is hot. So the idea is that even in the simplest systems, there are changes in the state. So if you will start turning on and off a light bulb, eventually it will go off. So it will become broken. So repeating tests many times can uncover additional problems that will not be located by executing regression library once. And it is there is a call for this method. It is long running regression. So the first thing that we can do, we can run the tests many times. The second one is called load enhanced functional testing. It is when we run functional tests but under load. The idea is that due to race conditions, states accumulation, other things, the result under load and without load can be different. And an interesting point here is that in production, in real life, most of the systems are always running under heavy load. Well, so most interesting systems are running under heavy load. So realistic test scenario is always load enhanced. And the most interesting defects are located at the confluence of functional and non-functional testing. You can, of course, send lots of identical transactions and kill the system due to out of memory or due to out of disk space or inability to sustain the volume. But more interesting defects happen when the system is still alive, when it still has resources for processing, but things happen that will not be reproduced without load. So running functional testing under load allows not just stress the system, but to get more information about it quicker, because we can run many tests in parallel and get more information about the system under test. So even by repeating the systems in the tests in time or across the space in parallel, the same test, we can get more information. But even better results can be achieved through parameters variation. So if we will allow software to prepare tests that will vary parameters, we'll get more output from our testing, we are more likely to hit a narrow or random problem in the software. There are many techniques based on this approach, including fuzzing. But one thing is that what we would like to have is to try to understand whether the system is okay or not. It is easy to understand when the system is not okay, when it crashes, but in order to have ability to say that something is not okay, when we vary parameters, we need to have additional ways of automatically identifying whether something is requires investigation. Thanks a lot for watching it on this YouTube channel. We have additional videos on it, on the subject, and in particular, I recommend you the one on test oracles. It is from our Global Exchanges FinTech webinar, where it contains more detailed explanation what are test oracles and how they can be used in conjunction or with high volumes of automated testing. Please do have a look. And test oracle is a method for determining whether a test has passed or failed. There is no perfect oracles, so all oracles are partial oracles. But when we have multiple partial oracles in parallel with high volume of automated testing, we can be alerted when something is not right. So we need to use different types of oracles with high volumes of automated testing. So even if we put random load into the system, or even if we are not able to predict the exact outcome of non-deterministic system, we still be notified when something is not okay. So in order to be able to run efficient high volumes of automated testing, we need to rely on oracles. And the stronger your oracles, the better would be the results obtained through using this technique. And all testing is model-based testing, but in some cases you can use models or simulators as oracles to understand whether the system behaves in an unremarkable way or whether it is necessary to alert a software tester. We can use similar systems, previous versions of the software, constraints, rules, and diagnostics, and many other things as test oracles. So what is a similar system? If we have some software that performs the same functionality, what we can do with our zillions of tests that we are executing in high volume fashion, we can execute them against our system under test and similar system under test, and then compare the output. This way we'll be able to see if it is indeed similar or there are some discrepancy. A good example of a similar system can be the previous version of the software, where we can run with thousands of scenarios or millions against the previous version. Constraints and rules can highlight something that is independent of the input and identify correlations within the data streams that highlighted there are errors or problems. And diagnostics is very important. For example, you may not predict some particular negative case or some particular scenario that will trigger a bug within the software. But what you can do is, when you run high volumes of automated testing, you can collect all log files and grab them, search them for exceptions. And this can serve as a model and an oracle. So our system should not output errors or warnings to the log files under normal operations. And if it happens, then something is wrong, or particular types of messages. So there are many ways of getting information from the system, but for high load, low latency solutions, even such things as comparing two similar systems or comparing version to the previous version has many challenges. Then there is a research paper and white paper available on our website or published in scope of TMPA conference that describes what are the challenges of comparing different versions, why it is affected by many distinct factors and timing and various events, etc. So if you would like to understand better what can be the problems with analyzing the output of high volume of automated testing, please do have a look at these papers. So what are the key requirements for the platform capable of doing high volumes of automated testing? It should be able to execute arbitrarily many tests and process their results. It should be able to run in many configurations and go through extreme number of permutations. In order to do it efficiently, it needs to support high volumes and parallel test execution in order not just to run and see that the system is still okay, but to extract valuable information, we need to have ability to apply multiple test oracles in parallel for various of our tests. So we simultaneously put extreme number of tests, and at the same time we apply many different oracles to these test scenarios to see if it is necessary to alert the system's operator, the software tester. And also the reference platform should have macro level resilience, because quite often when you do things, something gets broken. And when you run millions of tests, you need to find a balance between a single broken test and millions of other scenarios that you still need to execute. So the reference test platform needs to have macro level resilience. We do have a reference platform now available in open source. It is called TH2, but probably I will cover how to use it to implement high volumes of automated testing in our next lecture at Global Exchanges FinTech webinar. I hope you find some of information, or at least links, in this presentation relevant and useful for you. Thank you very much for your time.
Thank you, Iosif, for the interesting presentation. I see a question in the chat, so I will read it for you. Can running several same tests at the same time may cause a pesticides paradox?
Absolutely. So it is one of the reasons why we need computer assistance to vary parameters, to achieve parameters variation. And when we do standard test automation where human design all tests and their results, it requires human effort to modify scenarios to avoid things like pesticide paradox. But if we are working in a manner where we generate arbitrarily many scenarios with different parameters every time, we are less likely to be affected by the effects of pesticide paradox. So it will decrease its impact, but still, of course, it will just move it to the next level. So it will be more, our cure will be better to these types of bugs. But there's, of course, if we will not modify the models that we use to generate scenarios, eventually we will encounter pesticide paradox on the next level. It's very good question. Thank you.